All right, let's see. All right, so can everybody hear me or what? Yes, Noah.
Yeah, you're good.
Hello. Can y'all hear me?
Yeah, you're good. I can hear you fine.
Okay, great. Okay. All right, so yeah, just an announcement. Because of this hurricane thing, how we lost the day of class. I don't know if y'all saw the announcement and email that I sent out, but the tests and the homeworks and all that stuff, they have been pushed until next what is it? I believe 9/2, September 2nd. Yeah. So your test will be that day as well. And you'll start the test at 4 o'clock and you'll have like an hour to take it. Okay, ample time to finish it up. And afterwards we'll have lecture and all that good stuff like that. Now, really important, if you haven't done the Respondus Lockdown browser initial quiz, again, that's just a test to see whether or not it's working on your computer. Please do it, right? It's due by this Saturday. It doesn't count for a grade. The main thing is to make sure that it's working on your system, your computer, okay? You don't want to sit there and then try to figure out what it's doing or why it's not working the day of the test, okay? So you can't wait until the last second, all right? Now, let us start with 2.6. And at the end, if you have any questions about anything from the previous assignments, feel free to ask me, okay? So we're still dealing with limits. Remember, that's one of the three things, the three major things that you talk about in Calc 1: limits, derivatives, and antiderivatives. In this section right here, we're dealing with infinite limits or limits at infinity or negative infinity. I'll just put plus or minus infinity. So remember, in the last section, what were we doing? We were dealing with limits of basically finite numbers, right? And we always had these issues, right? Like we first initially plug the number in and see, okay, are we gonna get something undefined, right? And if that was the case, meaning like you were dividing by zero or something, we had to algebraically manipulate our problems that when we plugged in that finite number, we would get a number that would exist, right? In this case, though, we're just plugging in either positive infinity or negative infinity. So basically, what's going on here is, if we think about it conceptually, if let me get another marker, if x increases, remember that means w slash o without, that means without bound, then x approaches infinity. Or I'm sorry, this should be y approaches infinity. Because remember, limits are about the journey, right? And infinity, those aren't finite numbers. It really means either a really big number or a really small number. And if x decreases without bound, then y will be approaching negative infinity. So, what's an example, a very straightforward graph of that? Like if we have f of x, say for example, equals x cubed. This is a nice little graph, and it does something, or curve, it does something like this, right? And as you can see, as x goes towards positive infinity, remember this is x right here. Where's y going? It's increasing without bound, right? This is going towards positive infinity. So we could say right here, oh, the limit as x approaches infinity of x cubed, it's going to positive infinity, right? Because you can kind of imagine, oh, we're on this trip. As I keep walking along the x-axis towards positive infinity, where's my y going? It's going up and up and up forever and ever and ever towards positive infinity. Same thing with the limit as x goes to negative infinity of x cubed. Well, the further I travel to the left along the x-axis towards negative infinity, my curve is going down, down, down forever towards negative infinity in this instance. So that's what we mean by if x increases without bound. Basically, there's nothing holding it back. It's going to blow up forever with respect to y. Same thing with if it decreases without bound, it will continue to go downward towards negative infinity. And again, infinity and negative infinity are not finite numbers, right? They just conceptually mean if it's positive infinity, a really large number, or for negative infinity, it's a really super small number. That's very important to remember, especially in this section right here. Now, what if we checked out a graph like this? Like if we look at that, f of x equals 1 over x right here, and we want to find the limit as x goes to negative infinity of f of x, and also the limit as x goes to positive infinity of f of x right here. So these, let's graph it first to see conceptually what's going on with it. So the graph of 1 over x looks something like this right here. So if you're to make a t-table and choose values, you see that this is what your curve basically represents right here. So did you have to remember what this thing looks like? No, but it helps though. But again, if you're always lost about how a curve looks, you can make a t-table. Now you notice a couple of things, right? There's a couple little strange things happening right here. Is that first of all, it's not continuous, right? For some reason, mystical reason, there's no, our curve doesn't cross or exist at y equals 0. I'm sorry, x equals 0. Why is that? Because what happens if you were to plug 0 in for x right here? You get 1 over 0, which is undefined. Remember, undefined means does not exist. But this actually goes back to the previous section, right? Like if you have some kind of imaginary vertical uh, wall, this is a vertical asymptote, right? At x equals 0. Where do we get x equals 0 from? Did we just make it up? No, it's because remember, vertical asymptotes from Math 130, it comes from setting your denominator equal to 0, right? And you solve for x. So setting denominator equal to 0. Well, what was your denominator just in this case? It was x equals 0. So that's where that comes from. But this other one, if you notice, there's like a horizontal wall, right? It looks like our graph is flatlining along y equals 0 right here. But as you can see, if we were to continue drawing the sketch towards negative infinity or x equals negative infinity, like we're examining this first problem right here, the limit as x goes to negative infinity or approaches it, where is f of x going, or where's y getting closer and closer to? If we kept walking along, our curve right here, we slowly get closer and closer to y equals 0. Remember, limits are about the journey, right? You keep trudging along to the negative infinity step, you'll get closer and closer to y equals 0. Same thing with, well, what about the limit as x approaches positive infinity? We keep walking along the x-axis towards the positive infinity. Again, our curve's flatlining, right? It's getting closer and closer to y equals 0, or it's approaching y equals 0 right there. Now, again, this is a unique one, just like if you have this purple line was a vertical asymptote, straight up and down, one that runs left and right, this is just called a horizontal asymptote. So if we have, if the limit as x approaches negative infinity of f of x equals some value L. Like in this case, it was 0, correct? When we went off to the left side. Or if the limit as x approaches positive infinity of f of x equals some limit, then the line y equals L is a horizontal asymptote. I'm going to put HA, okay? That just means horizontal asymptote, all right? HA means horizontal asymptote. Or if I say VA, that means vertical asymptote. Or write down VA, that means vertical asymptote. Is a horizontal asymptote of the graph. So anytime you see some kind of flatlining occurring like that, from left to right, anywhere on a curve, that's a good indicator of a horizontal asymptote. Can you have more than one horizontal asymptote and vertical asymptote? Yeah, it's totally possible. It just depends on what your curve looks like. Now, one that's important to remember, you should remember this because it comes up in Calc 2, 3, wherever, never, never, is this one right here. Like if we have f of x equals arctan of x, and we want to find the limit as x goes to negative infinity of f of x, and the limit as x goes to positive infinity of f of x. Now remember, arctan is an inverse trig function, right? It's not a normal trig function. Normal trig function is like sine, cosine, and tangent. When you have that little -1, right, that means arc, right? Arc or inverse of that specific trig function right there. So what does the graph of this look like? So I know you don't have a graphing calculator, but as I said, this is the one inverse trig function that you should commit to memory. So you're thinking negative infinity, positive infinity for some kind of trig function. I remember from older math classes that the trig functions usually bounced up and down, right? They're kind of wavy. So how's this going to make any sense? But arctan is a unique case because the graph of that does not actually bounce around. It actually looks kind of like a sideways x cubed, kind of like that. This is x, this is y. But you notice though, we have that flatlining motion happening as it goes to the left and to the right. And what does that mean exactly? Well, we have two horizontal asymptotes. That means they are being bounded by something, right? As x goes to negative infinity and as as x goes to positive infinity. These horizontal asymptotes are finite numbers. This is actually pi over 2. Y'all remember that good old pi is 3 pi over 2 pi over 6, all that good stuff? Yeah, it comes back. You got to use it. And this one is negative pi over 2. Again, remember this right here, okay? This arc or inverse of tangent comes up a lot, not just in this math, but in Calc 2 a million times, okay? You're going to integrate it, derive it, all that good stuff. And it's important to remember that it is bounded between pi over 2 and negative pi over 2 for its range like that. So knowing that though, if we were asked to examine the limit as x goes towards negative infinity, well, if we keep walking along the x-axis towards negative infinity, your line is getting closer and closer to negative pi over 2. Now, for the limit as x approaches positive infinity, if we keep walking along the x-axis towards the positive infinity, our line with respect to y gets closer and closer to positive pi over 2. So we can label this as well. This is y equals pi over 2 and y equals negative pi over 2, like that. So you need that y equals because that's what gives us the horizontal line, right? Just like x equals gives you vertical lines. And on WebAssign, be careful because when it asks you for asymptotes, like a vertical, they may already have in the answer box x equals, for example. So you don't need to type in x equals and then your numbers, right? Because if you do, we get it, right? Because we're not computers. We get, oh, this person's trying to say that's the vertical asymptote. But the computer will see 2x equals, and it's not going to understand that, and it's going to think that you're wrong right there. So just make sure, you pay attention to the input and how stuff needs to be entered inside those answer boxes. If a mistake like that does come up where you typed in the correct answer and you have the right numbers and stuff, just send me, an email through, not through Zoom, but through WebAssign, and I can go in there and manually give you points for those particular problems. So again, remember this. This is the graph, right? This does exist right here. Arctangent does, or inverse tangent, they mean the same thing. They do have limits that exist at negative infinity and positive infinity. So we're going to check out now, because we looked at limits at infinity, but what about if we take limits, or look at limits of polynomial functions at, I'll say, plus or minus infinity, either or, right? So we kind of did look at that initially, right? Like we looked at, say, if you recall, f of x equals x cubed. We saw that, right? Like, oh, the limit as x goes to infinity of f of x was positive infinity, right? And then we had this limit as x goes to negative infinity of f of x was negative infinity. And again, we saw that from the curve, right? Like that made sense right there. And this is a polynomial function, right? I mean, technically it is a monomial because it's one term, but it still is or behaves like a polynomial function. Now, what's really important is that when you have polynomials, which is more than one term, right? We kind of have to be careful. Limits, or I'll say infinite limits don't follow the limit laws since infinity is not a finite number. So remember, I said it before, infinity and negative infinity, I'll put plus or minus right here. Infinity and negative infinity are not finite numbers. It just means a really big number or a really small number. So why is that a problem right there? Like say if I have, for example, the limit as x approaches infinity of x squared minus x, for example. Something like that. That's a polynomial, right? Now, what's the problem? You're maybe thinking, oh, I can just plug infinity in, right? Like I can just go, oh yeah, this is infinity squared minus infinity. Bam, that's got to be infinity, right? I'm done. Like, no, that not true, not true at all. But I'll just put false. You can't do it like that. Why can't we do it like that right there? Because remember, infinity just means a really big number, and no two infinities are equal. So you can't assume that, oh, this infinity is just equal to this one right here. It's the same exact infinity. So if I'm squaring infinity right here, right? Like if I'm squaring a really big number, I get an even bigger number, right? And if I subtract a really big number, well, this one's got to be bigger, right? So I'm left with something that's going to be positive, right? Again, we don't know how big these numbers are, so we can't make that argument. So what we have to do is go out there and rearrange this problem or rearrange it algebraically. This right here, for example, when you see things like infinity plus or minus infinity, or if you something like that, or infinity over infinity, stuff like this, these things are called indeterminate form. So indeterminate means, again, we can't determine, is it going to infinity, negative infinity, zero, some other finite number. And again, the reason why is because no two infinities are equal right here. You see, like in this case, this could go to this first one, this could go to zero, or it could go to positive infinity. It just depends on which infinity is bigger, right? Or in this case, when we divide, for example, depending on which infinity is bigger, it could go to infinity or zero, right? Like if this infinity was like say equal to 5 and this one was equal to 50 million, yeah, it's going to be closer to zero, right? Or if I flip that, the reverse of that, for example, then it would be going to positive infinities. That's what we call it indeterminate form, because we can't guarantee in these current forms, oh yeah, it's going to infinity or negative infinity or zero, or it's just undefined. So we're going to have to do some kind of manipulation right here. But what are we going to do? So if you notice, I didn't have any kind of product. I didn't have like a product right here, right? What I could do though is I could say, oh, I'm going to factor out an x. Now, if I factor an x out of this expression, we're left with x minus 1, right? So now, why did I do that, right? Like, why did I do that? Well, if I take the limit now, remember, infinity just means a really large number, right? If I were to plug this in, we get infinity times basically infinity minus 1. Remember, infinity is not a finite number. It just really, it means a really big number. So the way you can approach this is say, okay, I have a really big number here. Now I have a really big number minus 1. But a really big number minus 1, well, this little chunk here is still a really big number, right? So this is infinity times infinity. But if I take a really big number and I multiply it by another big number, what do you get in the end? You still get a really big number. So the limit does go towards infinity in this case. This would be your final answer right here. So what you're trying to do right here with these polynomials is conceptually break it down into the product of something. Because in the end, what you're hoping for is, oh, I have a really big number times maybe a negative finite number, or a big number times another big number, just like what we did right here. And then from there, you can say, oh, it goes towards positive infinity or towards negative infinity, for example. But that's what you're trying to do, convert your polynomial expression, this, right? You want to convert it into the product of terms. That's what we're looking, or what we're trying to do. So like what if we had, for example, the limit as x goes towards negative infinity this time of 1/3 t to the fifth plus 2t cubed minus t squared plus 8. So again, with this polynomial, we can't just plug negative infinity to all threes because we're adding and subtracting right here. But if we can somehow rewrite it as the product of two terms, then we'll be okay. Now, how to do that? You're just factoring out. Now, what you're going to always factor out is, don't think GCF, greatest common factor. You want to factor out the highest power variable. That's what you always want to do, okay? You can try to pull out the constants if you want, but that ultimately in the end doesn't matter with infinite limits. It's the highest power variable. So we're going to pull out a t to the fifth. If I do that, this becomes 1/3, right? Now with these, remember, factoring out means dividing out, right? So if you factor out the t to the fifth from a t cubed, you would wind up with 2t to the negative 2 power, right? Because you're dividing the exponents out or subtracting. So 5 minus 5 gave us 2 to the 0, which is 1. Or 3 minus 5 gives you t to the negative 2. With the t squared, you're going 2 minus 5 gives you a negative 3. And then this, well, there's no t right there. You could say, oh, there's a t to the 0. So we have plus 8t to the negative fifth power. I know you probably think, well, this looks worse. What is this t to the negative 2, t to the negative 3, all those negative exponents do? It makes it look horrible. If I plug negative infinity in here, aren't I still going to get infinity? No, because what if we rewrite this? Remember, we don't like negative exponents, and you should never write your answers with negative exponents. You should eventually convert them to positive exponents. And you can. Remember, if I convert this to a positive exponent, what's the trick? You just flip the thing that the negative exponent is being applied to. This becomes 2 over t squared. This becomes 1 over t cubed. This becomes 8 over t to the fifth. Now, why not flip the 2 or the 8 right here? Because was there a negative exponent being applied to this particular 2? No. Was this negative 5 exponent being applied to this 8? No. That's why these constants stayed up top. All right. So we still have this limit, right? We still have this limit as x goes towards negative infinity. Now what happens if we plug in the negative infinity? I mean, you can see right here we have this negative infinity to the fifth power, and then you have 1/3 plus 2 over negative infinity squared. And we see, oh, we have all these little infinite limits. What are we ever going to do? But what the great part is, this is all very simple right here. So let's think about this. So you have a constant over a really big number, right? It doesn't even matter if it's positive or negative. If I have a constant over something that's super big or super small, remember, if you take your calculator, if I said 2 divided by a million, you're going to get 0.000, something. If you take 2 over a trillion, you're going to get something even smaller or that's closer to 0. So all these, anytime you have a constant, like a constant over plus or minus infinity, easy rule, it automatically becomes 0. Because think about that, right? A constant divided by a really big number is still going out to 0 or approaching 0. A constant divided by a really small number or negative infinity is also going to 0. So this is 0, 0, 0. I mean, you can put plus 0, minus 0, doesn't matter, but it's because it's 0. But remember this right here, a constant divided by plus or minus infinity, when you're dealing with infinite limits, it always goes to 0. That's great. We'd love if every problem could do that because look, no work, right? Now, what about this one though? Negative infinity raised to the fifth power. Well, The sign is important right here, right? It's a negative. Now remember, when you have a negative raised to an odd power, what are you ultimately left with? Like a negative number, right? Now, does it matter what the number is in this case? No, this just means a really small number, right? Or you could really say, you could think of it as a really big negative number. But if I take a really big negative number, and I multiply it times itself 5 times, I don't know what the number is. I don't need to know, but I do know its sign, right? This is still negative infinity. It's still negative, right? If it's a negative raised to an even power, right? Like again, negative infinity raised to the 100th power, 100's even, it would still be positive infinity in the end. So now we have this negative infinity times a third. Well, this is okay. So negative infinity times a constant, a really small number times a constant. Well, what's a negative times a positive? It's still a negative. And it's going to wind up being negative infinity. If this was positive infinity times any constant, it'd still be positive infinity. Or if you had infinity times infinity, that's infinity, right? Why? Because a really big number times a really big number becomes a bigger number, right? Or if you had something like negative infinity times infinity, think about that. What's that going to be? Well, I have a really we know it's going to be some kind of big number, but ultimately in the end, is it going to be negative or positive? Well, it's got to be negative, right? Why? Because a negative times a positive is just it's a negative, so you get that right there. So remember, think of infinities as really big numbers, or if it's negative infinity, really small numbers. But again, with these polynomials right here, we have to convert it somehow into the product of terms, because unfortunately we can't just plug in infinity and negative infinity into the polynomial because those don't follow the limit laws, right? Remember, in order for you to just be able to jam something inside, it has to exist and be in the domain of that particular function. But infinities and negative infinities, they don't mean it just means a big or a really small number conceptually. They're not finite numbers. That's why we can't just plug in the infinities in here and work it out like that. Don't forget this little trick right here with the factoring out of the exponents. How we do that, you're just subtracting. 3 minus 5 was negative 2. 2 minus 5 was negative 3, like that. If you're in doubt about this, you can always distribute back, right? Like if I multiply 2 to the 5th times 2 to the negative 2, remember with exponents, when you multiply, what do you do with them? You add. So 5 minus 2 is 3, or 5 minus 3 is 2. You can always double check that. Let's try another one. We'll say the limit as x approaches infinity of 2x to the fourth minus x squared minus 8x. The same like the last one, right? It's a polynomial. And this time we're looking at it as it goes towards positive infinity instead. Again, we can't just plug the infinity in because it's not a finite number. You can only plug, like if it was a limit as x goes to 5, for example, well, we can plug 5 in here, right? It's a finite number. It doesn't cause any issues where it's undefined or anything. So you would just plug the 5 in and crank it out, right? That would be okay. But in this case, we can't do that. So what do? We have to write it out as a product of two terms. Now, just like the last problem, we're going to factor out the highest powered x. Well, in this case, it is x to the fourth, right? So let's do that. Let's pull out an x to the fourth. If you factor out an x to the fourth, what are you left with? 2 and then minus. If you factor an x to the fourth out of an x squared, well, you're left with x to the negative 2 power. Remember, you're just saying factoring out means dividing out, so we're subtracting. 2 minus 4 is negative 2. Now with this one, we still have the 8. But remember, there's a 1 up here, right? They don't put anything. So 1 minus 4 is negative 3. Now remember, just like the last problem, what do we do with these negative exponents? We made them positive. So now we have x to the fourth, and then 2 minus 1 over x squared, and then minus 8 over x cubed. Remember, this 8 does not get flipped because it does not have a negative exponent being applied to it. That negative 3 only applies to the x. If you wanted to get super technical and you said, oh, what powers the 8 have? It has a 1. It's positive, right? This is positive, so we're not going to flip that. If it was 8 to the negative 1, yeah, you'd flip that thing as well. But we don't have that in this case. So now if we jam infinity in, remember what's going to happen right here. We basically get infinity. I mean, you can write it in if you want. Infinity to the 4th, and then 2 minus 1 over infinity squared minus 8 over infinity cubed. Now remember though, what did we mention before about a constant over infinity or negative infinity? Where do those go? Zeros. This becomes zeros right there. Now you're left with infinity to the 4th times 2. Well, now this is the part where you start thinking, okay, infinity means really big number. If I take a really big positive number and I raise it to the 4th power, what happens to it? It just becomes even bigger. So this is still infinity. This is still 2. Okay, so now I take a constant and I multiply by a really big number. What do you get in the end? You still have a really big number. Even if this was a fraction, okay? If you had like 1 over 50 times infinity, just because you're dividing by 50, that's not going to make a really, this is a super huge number, right? It's not going to affect it. It'll still be infinity. So remember, infinity times any kind of constant, if it's positive, is positive infinity. If this is negative 2, like infinity times negative 2, well, positive times a negative would make it negative, correct? So it would be negative infinity in that case. Remember, that's what you want to do with the polynomials, okay? You want to try to write them out as the product of 2 terms. And then once you're there, please watch the signs, right? Especially if this is a negative infinity. Remember, if you have a negative number, a negative number raised to an odd power, it's still negative, correct? And if you have a negative number raised to an even power, it is positive. All right. So those are polynomials, though. What about rational functions, right? Like limits. Limits of rational functions at plus or minus infinity. So remember, rational functions are like fractions, right? That's an issue right there. Like let's say we had, for example, we want to find the limit as x goes to infinity of 3x minus 7, for example, over 2x plus 15. I mean, it really doesn't matter, okay? I'm just making this up. So we have a problem here. What's that problem? Well, if you remember what I first mentioned when we first started getting into this, is that we can't just say, oh, this is infinity over infinity, haha, and then this is 1, right? No, because these two infinities definitely aren't equal. It's not even the same equation, right? So this is indeterminate form. Again, that's indeterminate. Because remember, depending on which one's blowing up faster, if the top is blowing up faster than the bottom, your limit will go towards positive infinity. If your bottom was blowing up or increasing faster than the top or the numerator, then your limit would be going to 0. And of course, it could go to something else too, just depends on what's happening. So how do we go out there and find the limit or infinite limits of rational functions? How do we do that right there? So the limit of a rational function as x approaches, I'll put plus or minus infinity, is the limit of the rational function divided by the highest powered, or the highest power of x from the denominator. All right, so how are we going to approach this then? How will we do it in this case right here? So it says the limit of a rational function as x approaches plus or minus infinity is the limit of the rational function divided by the highest power of x from the denominator. That's very important. So basically, you got to look at or ask yourself, what's the highest power of x in the denominator? Well, in this case, this is it right here, right? This is it. That's the highest power of x is x to the first. You don't care about anything else, okay? You don't care about the constant right here. You don't care about that. You just care about what is the highest power of x in the bottom. You don't care about what's happening up top at all, about what's the highest power, whatever. So it says we have to divide everything divided by the highest power of x from the denominator. So what you're going to do is you're going to take your entire rational function and we're going to divide every single term by this x to the first right here. That's what we're going to do. And again, it's because the x to the first is the highest power in the denominator, not the numerator, in the denominator. So what happens right here? Well, we can start knocking stuff out, right? If you notice, this goes away, this goes away, like that. And then what's left over? Well, now we have the limit as x goes to infinity of 3 minus 7 over x minus, I'm sorry, over 2 plus 15 over x. Now, if we plug the infinity in, are we going to have any issues? Are we going to have infinity over infinity? No. So remember, what happens with this, when you plug infinity in over here, or into these little fractions, what do you wind up with? Zeros, right? This is, you don't have to do this step. Over time, you'll realize it. You can do this for now if you want. Remember, what happens to a constant divided by plus or minus infinity? This goes to 0. This goes to 0. So what are you left with? 3 halves. So your limit in this case as x goes towards positive infinity is 3 halves right here. This is actually also, too, a horizontal asymptote, right? This is y equals 3 halves. Likewise, if we were to go to negative infinity, or as x approaches negative infinity, you'd still have y equals 3 halves right there. Remember, when you get a finite number, when you take an infinite limit, like where finite means like you get to it, right? This this indicates that that is a horizontal asymptote. Remember the line that runs left and right of that particular rational function. Remember, the trick is divide everything by the highest power from the denominator, not the numerator. Let's try the limit as x goes to negative infinity of x minus 2 over x squared plus 3x plus 1, for example. So again, if we plug negative infinity into here, you get negative infinity over infinity, right? Still undefined, right there. It's indeterminate form. So the trick for the rationals again is divide everything by the highest power variable of x in the denominator. So what is that? This guy right here. If this was negative x squared, guess what? You still divide by x squared, okay? That's what you do. You don't care about the coefficients or the numbers in front of the variables. You just care about what is the highest power x in a denominator. So if we rewrite this with everything being divided by x squared on the top and bottom, remember everything gets divided by the x squared. What can happen, or what we should always be able to do, is simplify things. Definitely we can. So x over x squared, that just becomes 1 over x, right? So we have 1 over x minus 2 over x squared. Can't do anything with that in terms of simplifying, so it's just that. X squared over x squared is 1. 3x over x squared becomes 3 over x. And then 1 over x squared is just 1 over x squared. So now we have to throw in this negative infinity, right? So remember, whenever you have a constant over plus or minus infinity, where is that going? That expression, that value, going to 0. So 1 over a constant, what is that going to? That's going to 0. 2 over a constant, where's that? I'm sorry, 2 over negative infinity squared, that's also going to 0. This negative does not affect this at all because a constant over infinity or negative infinity is still 0. So we have 0 minus 0 up top. On the bottom, no x right here, so that's 1. 3 over x, as x goes towards negative infinity, it's going to approach 0. Same thing with the constant over x squared, that will also approach 0. So you see, now we have a bunch of zeros. We have 0 up top and 1 on the bottom. What's 0 divided by 1? That's not undefined, right? That's actually 0 right there. Remember, the issue is when you have anything divided by 0. When 0 is in your denominator, that's when you'd have a problem, right? But we didn't have that right there. So your limit right here does exist. It is 0. And you could also say, oh yeah, I have a horizontal asymptote at y equals 0 in this case. So remember, you always divide by the basically it's like the dominant term. That's what we call it as well. The variable with the highest power from the bottom, because that's what ultimately controls how your curve or line will behave. Now, what if we have like a root, right? Square root someplace. How do we do that? All right, so we have limit as x goes to infinity of root x plus x squared over 2x minus x squared. So in this case right here, still can't we can't just plug in infinity because we get infinity over infinity. So we're gonna have to go out there and again divide everything by the dominant term from the denominator. What is it? This is the dominant term, right? The variable with the highest power, x squared. Don't worry about the negative. We just care about it's gotta be x squared. Now, how are we gonna do that? Like, how are we gonna divide that out with the root? Well, looking at this root right here, remember, these are all exponents, right? The 2, there's a 1 right here. You can rewrite the square root of x in exponential form. Remember, whenever you have the nth root, this is very important, right? Y'all should remember this right here. If you have the nth root of x, this is x to the 1 over n power. Remember, the index becomes the denominator of your exponent. So, why is that important for this problem? Because now when we write it out, right, when we divide it out by the x squared, we're going to change this to x to the 1/2 instead. So you have x to the 1/2 over x squared plus x squared over x squared over 2x over x squared minus x squared over x squared. So if you're dealing with limits, and you have roots, sometimes if they're, especially if they're by themselves, meaning they don't have anything else inside, then you want to convert it to exponential form. Now, if it was like the square root of, x cubed minus 5x plus 10, don't convert it to exponential form. You have to work it out a different way. And we'll look at one like that next section. So remember, at this point, we can simplify, right? Like these two are easy right here. This is 1. This is minus 1. 2x over x squared is 2 over x. Now, what about this one? Don't freak out. Say, oh, fractional exponent, what do I do, right? Remember, it's the same thing as what we've been doing right here. How did I get this 2x right here? You're just dividing out the exponents. Remember, you're subtracting. You're subtracting the exponents, right? It's always top minus bottom. So if I did 1/2 minus 2, you can say that's x to the negative 3/2 if you really want to, right? I'll put that right here. This becomes x to the negative 3/2. So you can say, oh, that's 0.5 minus 2. What's 0.5 minus 2? It's negative 1.5 or negative 3/2. But since that's a negative exponent, we can flip it, right? And we write it as 1 over x to the 3/2. Now, if we were to plug infinity in, will we wind up with infinity over infinity? No, which would be indeterminate form. We're going to get something that does exist, right? Because what's a constant over infinity or a constant over infinity? 0, right? That goes to 0, 0. What are you left with, though? 1 over negative 1, which is equal to negative 1 right there. So watch the signs, right? Positive over negative is a negative. Watch the signs with that right there. So again, if you have a single root, right? Single root, or a single term under root, convert that thing to exponential form. So this is the fifth root of x, so you'd have x to the 1/5, right? That's what you would do right there. If you have multiple terms under that root, like x plus or minus something or whatever, you don't do that right there. We're gonna have to work it out a different way. That's what we're gonna check out right now. So again, we have infinity over infinity, right? If we were to put that in there, that's square root of infinity is still infinity, right? Square root of a big number, still a big number. So that's indeterminate form. again, we're going to divide everything by the dominant term from the denominator. Well, the denominator, the highest power term is this, right? Now you may be thinking, well, how do I divide that out into this, right? Because that's trapped under a root. How can I do that? Well, let's think about it for a second. We can rewrite x cubed as a root, right? Like, what if I said x cubed is equal to the square root of x to the sixth, right? For x greater than 0. And we're going to positive infinity anyway. Is this legal right here? It is, right? Because what is the square root of x to the sixth? It's x cubed. So this is a really important trick to remember when you're dealing with infinite limits and roots sometimes, because sometimes you have to rewrite that denominator piece so that you can merge it or successfully take the limit and jam it inside of that root right there. And you can test it, right? Square root of x to the sixth is x cubed. So it is completely legal. That's just an algebra trick that we did. It's kind of like the trick of multiplying by the conjugate, right? It was just a fancy form of 1. This is just a fancier form of x cubed. That's just going to allow us to merge this and take the limit. So what is that going to look like if we were to do that? So for the denominator piece, because none of that is inside of a root, we're still going to divide everything by the x cubed. For that top piece, though, we're basically going to have the square root of 9x to the sixth over x to the sixth minus x over x to the sixth. So remember, you may be thinking, where did you get that x to the sixth from? Remember, the square root of x to the sixth is the x cubed right there. Basically, what's happening is remember, is this legal right here? Well, if I were to just work this off to the side again, like if I take this, if I take the square root of the top and the bottom, right? If I were to do that, I'm still left with the square root of 9x to the sixth minus x over x cubed. That would be like me dividing everything by x cubed, right? But remember, I don't want to divide this by x cubed because I can't, this does not help me out at all. Why? Because when I take this limit, you can't simplify these x's right here. Why? Because they're both not under the root. By us rewriting x cubed as the square root of x to the sixth, that allows us to get that x cubed inside with the root as an x to the sixth, so that we can successfully cancel stuff out and take the limit. So you see, you can always work backwards. If you're like, did I do this right algebraically? Simplify it, and if you get back to what you started with, then yeah, that is an algebraic trick that is legal as long as you simplify things correctly. Now, if we continue with this, right, what happens right here? Well, this becomes 1, right? So we're left with 9. This becomes 1, right? Now, if we reduce this stuff, what are we left with? We now have this limit as x goes to infinity of the square roots of 9, right? Because the x squareds go to 9, so they're minus 1 over x to the fifth divided by 1 plus 1 over x cubed. So where that 5 come from? Remember, this is x to the first. Top exponent minus bottom. 1 minus 6 is negative 5, but x to the negative fifth, when you make it positive, you flip it over and it becomes 1 over positive x to the fifth right there. Now, if we plug this infinite limit in, are we going to get infinity over infinity? No. You wind up with the square root of 9 minus 0. Remember, constant over infinity is 0 over 1 plus constant over infinity is 0. So this is square root of 9 over 1, but then that gives you 3, right? That is the limit of this right here. The answer is 3. So again, important. Remember that trick, right? Remember that trick. Oh, I got to rewrite the root, rewrite that x function with the root, right? Where did I, is that legal right there? It is. It's because if I take the square root of x to the 6th, we are left with x cubed. Why do we have to do that? It's so that when we took the limit of this particular function, we were able to embed or get this x cubed inside the root. But in order for me to get that x cubed inside the root, I also have to write this as a root. So this is x cubed in its equivalent root form. That's why we had to do that right there. Let's check out another one like this. So here we go. The limit as x approaches infinity of x squared over the square root of x to the 4th plus 1. All right, so again, got to divide everything by the dominant term from the denominator. It's this, right? Be careful though. It's inside of the root, right? It's inside of the root. So that root also applies to this. So in this case, right here, the dominant term is the square root of x to the 4th. Really important, we had to include the root, right? It was trapped in there. Now, how's that going to help us with this problem? Well, what is the square root of x to the 4th? That's equal to x squared, right? If you want, in this case, you could sit here and say, yeah, I'm going to divide everything by the square root of x to the 4th, if I wanted to do that. But you can write it like that if you want. But then what you'll see from here is that, oh yeah, this is x squared over x squared, right? Because the square root of x to the 4th is x squared. What are you going to do right here? Well, because now both of these are under roots, you can merge them into one big root. Like that. All right, so let's see. We divided everything. Now it's time to reduce. Well, we have 1 over the square root of 1 plus 1 over x to the 4th. So now if we take our limit as x goes to infinity, we don't have any problems, right? We don't have infinity over infinity. So this becomes, this is still 1 over square root of 1 plus, remember, constant over infinity or negative infinity, it's still 0. So now you have 1 over the square root of 1, which is just 1 right there. All right, so now we're back to, it's still a rational expression, right? If we plug negative infinity in, you still wind up with some variation of infinity over infinity. No good, right? Because that's indeterminate form. So what do? We divide everything by the dominant term from the denominator, which is x cubed, right? That's our dominant term right there. Let's do that and see what happens. All right, so let's simplify, right? Like right here, what do we get? You actually have x when you simplify that, right? 4 minus 3 is positive 1. This is 3 over x. 2 minus 3, right? X squared over x cubed. 2 minus 3, top exponent minus bottom. 2 minus 3 is negative 1. But we'll make that positive by flipping, so we get 3 over x to the first. This becomes 1 over x squared. Again, because you have 1 minus 3 is negative 2. X to the negative 2 is 1 over x squared. Right here we have 1 minus 1 over x squared plus 2 over x cubed. So remember, we're plugging negative infinity in, right? That's what we're plugging in this time. Let's check that out. If we plug negative infinity into this, well, what do we wind up with? We have, let's go here. We wind up with negative infinity, right? And then we have, remember, constant over infinity or negative infinity doesn't matter. It's still 0. So this is minus 0, plus 0 if you want to do that. At the bottom we have 1. This is minus 0. This goes to plus 0. And if we keep simplifying, what do we get? We get negative infinity over 1. This is okay though, right? Whenever you have infinity divided by or multiplied with some kind of constant, you can work that out. Because what is this? A really small number divided by 1. What is a really small number divided by 1? It's still going to be negative infinity in this case. All right, so this one looks kind of nasty, right? Like it says limit as x goes to positive infinity of arctan of e to the x. So it's kind of like crazy function trapped inside another crazy function. How do you take the limit? Well, whenever you have, functions trapped inside of other functions, what you do is you look at the inside piece first. So you start with that and you work your way out. Meaning, oh, let's see, what is the limit as x goes to infinity of e to x? What's going on right there? Then whatever's happening with that, we can apply the arctan to it. So if we had to look at the limit as x goes to infinity of say e to the x, just this right here, where's that going? Well, how can we tell? Well, let's think about this for a second, right? Conceptually, infinity is just a really big number. E is also a number, right? Remember, E is approximately equal to 2.71. So if I take 2.71, right, and I raise it to a really big number, where is it going? To a really big number, right? Positive infinity. Or if you remember the graph of it, also another way of doing that is does this. So we can see, yeah, as x gets larger and larger and larger, y is also blowing up without bound. So we can see that the limit as x goes to infinity of e to the x, it's also approaching infinity. Well, what does that mean? Well, if we know the inner piece, this guy here is going to infinity. Now we can say, oh, well, we have arctan of infinity. What is that? Does that not exist? Does it do something? Remember, it does exist, right? I mentioned at the beginning, this is a very important function. It will come up a million times. What does this do? This does have a limit. Remember, arctan does this right here. And it has a couple of horizontal asymptotes. This is pi over 2. This is negative pi over 2. So as arctan goes towards infinity, where is it going? The limit. It's approaching pi over 2. That is your answer right there. So again, if you have, a function trapped inside of another function, meaning like exponential trapped inside inverse function, or like an algebra function trapped inside of, a log function or something like that, you work the inner piece first, you figure out its limit, and if it's something, right, that does exist, like infinity or negative infinity or a finite number, you apply that number to the next part, and you keep doing that. If you got like a D and E, for example, like if this did not exist on the inside for some reason, then the whole problem is done. It just doesn't exist like that. All right. If we have something trapped inside of something else. Now, what about if we just looked at, say, the limit as x approaches negative infinity of, say, like, sine of x, for example, something like that. Where's that going? Well, remember, what's the sketch of sine of x look like? Remember, this is not an inverse function like this, right? This is just a regular trig function. It basically did this, right, as a wave. Right? That's what it was doing. It was wavy. I'll draw another little wave. It ran through 0, 0, right? And then its amplitude or a bounce between 1 and negative 1. Cosine also did the same thing, right? It was wavy. It's just that it runs through 0, 1 instead, but it still did that wave motion and it still bounced between 1 and negative 1 because its amplitude in this case was 1. So this is asking what's the limit as x goes towards negative infinity. So we kept, or if we keep walking along this x-axis towards negative infinity, where's our y going? Well, we can't say, oh, it's landing right at negative 1 or 0 or some number in between. So in this case right here, for like sine of x and cosine of x, if you're asked about its infinite limits, it does not exist because it oscillates, right? That just means bounces, oscillates between b slash t, right? Y equals plus or minus 1. It's not homing in on one finite value, unfortunately. So your answer would be D and E right there. But if it sometimes though, you have like a little trick case, okay? Like what if I had x approaches infinity of e to the negative 2x, and then cosine of x. Now let's look at this one. Well, you may be thinking, oh, that's infinity times a d and e or whatever. So it's d and e, or maybe it's infinity. But that's not actually the case, right? If you plug infinity into here, you don't get e to the infinity, which is infinity. Remember, e is a number, right? That's like 2.71. But this is a negative exponent right here. Remember, you have to make negative exponents positive. This is actually cosine of not 2x, of x over e to the positive 2x, right? That's what we have right here. So now if you plug infinity in, you may be thinking, well, for cosine of x, that's right. This would oscillate between 1 and -1. But what about this? When I plug infinity into the bottom, or e to the infinity, remember e is a finite number. If I take that and I raise it to a really big number, it just gets bigger, right? So this limit does not, it's not a d and e overall. Cosine of x, remember this is going to oscillate between plus or minus 1. This goes to infinity in the bottom. So remember, it's oscillating between plus or minus 1 cosine of x. Those are two finite numbers. Even if I said, oh, it goes to -1, what's -1 divided by infinity? It's 0, right? Because the constant divided by infinity is 0. What if it was 1 instead? Well, 1 divided by infinity is still 0. What if it's any number between -1 and 1? Like if I said, if it was 0.298561, well, divided by infinity, it's still 0. So in this case right here, the limit is 0. And the only reason why this works like this is because we were able to divide this right here, okay? So remember, the trick is, if you have some kind of tricky looking function like this, and it has a negative exponent, you gotta make it positive before evaluating that limit. All right, so that finishes up with 2.6. Let's get into 2.7. All right, so 2.7 is kind of like an introduction. I'll say intro to derivatives and rates of change. Derivative is actually just a fancy word for rate of change. It just means instantaneous rate of change. That's what the derivative means. But in working up to it, we're going to kind of talk a little bit about the theory as to how we're getting the instantaneous rate of change. All right, so let's just say we have some line, right? We start with some general curve here. And I'm going to have 2 points, okay? We'll have a P, point P, and a point Q. And I'll call this A, and this is X right here. We'll call this Y value F of A. And this X value for the Q, this will be F of X, the Y. So we could say point P is A comma F of A, and Q is the point X comma F of X, right? So there's like your x value, right? X comma y, right? That's what that is. Now, if we were to just draw, you know, like a line right here, right? A line connecting P and Q, right? A line between any 2 points on a curve is called a secant line. The slope of that secant line and I'll say between P and Q in this case, right here. Because remember, these could be any 2 random points on the line. And I shall put it right here up top. So m sub sec, that just means secant slope, right? Remember, m from y equals mx plus b, m stood for the slope. So how do we do that? Remember, for basic slope, remember we had, what was that? It was y2 minus y1 over x2 minus x1, right? Change in y over the change in x. Guess what? Same thing right here. So I'll call this, it's just going to be y2 minus y1 over x2 minus x1. Just like that. So we're going to have f of x minus f of a over x minus a. That's just the slope formula, right? Just following this, right? Like you could say this is your x1, y1, and that's your x2, y2. If you wanted to do it that way. It's the same thing, right? We're just calling it different letters this time. And of course, that slope, right, between these two dots, depending on where they are, it could change. It could be positive, negative, right? It could be undefined or zero, depending on, again, where these 2 points are related. So you've found the slope a million times before. You have been finding secant slopes since algebra 1, because that's what that was. This is always the secant line right here. It's just now in calculus they said, hey, we're gonna call it the secant line, a fancy word. So now, how does that apply to a derivative? Well, as I mentioned before, derivative means not just rate of change, but instantaneous rate of change. See, when there's separation between the 2 points, you have just a normal rate of change. You don't have an instantaneous rate of change. Instantaneous means, well, if I were to take these 2 dots and put them right on top of each other, like right on top of each other, that's what we mean by instantaneous rate of change right there. That's what gives us a tangent line. So basically what we're doing is we're taking this dot and we're moving it right on top of P so that there's no distance between them. They're right on top of each other. Again, that gives us the instantaneous rate of change. So what is that? It's a line drawn through only one point of a graph is a tangent line. The slope of a tangent is Actually, I'm gonna put it up here. So the slope of a tangent is the limit as x approaches a of basically y2 minus y1 over x2 minus x1.
Can you push it back up a little bit?
Yeah, sure. Got it? Good?
Yes, I can see it.
Okay. So now if you notice, we threw a limit in here, right? Now it becomes a big old calculus thing because we've got a limit in there. So conceptually, what's happening, right? So remember, we're drawing a line through only one point. As I mentioned before, normal slope is just rate of change between 2 points that have some kind of distance between them. But now we're looking for the instantaneous rate of change. Now let's think about this visually in our heads. The limit as x approaches a. So you take this dot q right in your head and imagine, oh, I'm slowly moving it closer to p, right? As I move this q point closer to p, what's going on right here? Look at the x. It's also getting closer to a. That's why we have this limit as x approaches a. That's what's happening right there. And again, we're trying to instantaneous rate of change means how fast something is changing at that one instant. So basically that one instant that we're trying to find this slope is when P and Q land right on top of each other. That's why we have this limit as x approaches a. Something else you may be noticing too is that, well, if x approaches a, remember, because x is a finite number, what do we do with stuff like that when you had a finite number? You would jam it into here, into your polynomial or rational expression and evaluate it. But check it out though, if I were to plug a into here, what would I get? You get a minus a, which is 0 in the bottom, which is undefined. So then you have to do that algebraic manipulation stuff. But that's what we do with the tangent lines. That's what it's allowing us to find. It's allowing us to find the instantaneous rate of change of a point, meaning at that one particular instant and nowhere else. So the secant one was basically this, right? That's when you had distance between 2 points. Instantaneous rate of change or tangent lines involve you finding the derivative or how fast something is changing at that one instant. Again, if we could somehow put this Q point right on top of this P point, right? And we want to figure out how fast it's changing. If you had to draw a tangent line at P, it would look something like this right here. It would basically kiss the curve at that one instant. This would be like a tangent line, uh, tangent line at P. So again, it's just basically a line that hits only one particular point at on the curve, and that's it. Just touches it that one instant. A secant line could touch it at multiple places because again, it doesn't care. It's just a straight line between 2 points. But tangents are very peculiar. It's just one point that your line, the screen line in this case, runs through on the curve. That's what we're trying to find out right here. That's what leads to the derivative. So let's try some of these. So we want to find the equation, EQ, find the equation of the tangent line. To fx or f of x at point P. So let's try f of x equals x squared minus 3x minus 5, and our point is negative 2, 5. Now, when you start these problems, what helps is let's label this right here. Remember back in algebra when they said, oh, find the equation of a line given a slope and a point, you label the point, right, as like x1, y1. Well, right here, we're not going to use x1 and y1. We'll say, hey, this is a comma f of a, just like that instead. Why? Because look at our equation. What does it involve? F of a and a instead of x1 and y1, for example. So, how do we work this out right here? Well, let's plug it in, right? Remember, in order to find the equation of a line, what do you need? You need a slope and a random point. We have the point. They gave it to us, right? -2, 5. We need the slope. So what is that going to look like in this case? Well, let's plug in all this stuff into this tangent slope formula. So we have the limit as x approaches -2 of, what is f of x? Well, according to this, it's this initial function, right? It's just the original function. You don't plug any numbers in. It's because it's saying throw f of x in. So we have this minus f of a. What is f of a? Well, f of a, right? Like if we work that off to the side, what is f of a? F of a is actually f of -2, right? Because a is -2 in this case. How do you find f of -2? You plug it into this equation, right? You plug it into here. So this is, and watch the signs, this is -2 squared minus 3 times -2 minus 5. So yeah, for your f of a in this equation, you will always plug that first value, which is like the x value, into your equation to spit out a number. This is 4, 4 plus 6 minus 5, right? So you wind up with 5. 10 minus 5 is 5. So f of -2 in this case is 5. And on the bottom, we have x minus, and watch the signs, right? Because it says x approaches -2, a is -2, so we're going to have minus a -2 right there. So let's simplify this thing. Now we have x squared minus 3x plus 10 over x plus 2. So we have a problem, right? Because what happens when we plug -2 into here? You get 0 in the denominator, which makes it undefined. I remember, what do we do with that when we had issues? We manipulated our equation algebraically so that we would not have that undefined issue going on. What can we do? Well, what was one of the things we could try out? Factor, right? We can factor out the top. If we factor the top out, we get x plus 2 times x minus 5. Well, that's great. Why? Because the x plus 2 is reduced. And now we have the limit as x approaches -2 of x minus 5. Well, if we plug -2 in, we don't have a problem, right? We don't have anything that's undefined. No issues, right? So we get -2 minus 5, which is -7.
How did we get plus 10? Shouldn't that be -10?
Well, what's -5 minus 5? Right? Like if I drop these parentheses right here, what's -5 minus 5? Oh, I'm
0.
sorry.
Yeah, it's -10, yeah.
Yeah, this is minus, right. So this is -10. It'll still factor into this right here. Sorry about that. Change the hit I. So yeah, this is -10 right here. This still factors into these two terms. 2 times -5 is -10. 2 minus 5 is -3. Like that. So we're still not finished, right? Because remember, the problem was asking for an equation, right? We need some kind of y equals mx plus b thing. what do we find right here? This is just a slope. This is just part of the puzzle, right? Remember, we need an equation right here. So where do we go? We have to use the point slope formula, right? Remember this, y minus y1 equals m times x minus x1. So remember, our slope's -7. We got that, boom, -7. We have our x1 and y1, right? What was it? Remember we had the point -2, 5? That becomes your x1 and your y1. Now watch the signs, right? Just like I tripped out on it so just now. So watch the signs. Y minus y1, that is y minus 5. And then again, -7 was our m, right? And then x minus a -2. Remember, we're doing this additional step because it asks for an equation on the line, not just what's the tangent slope, right? If it asks for just the slope that's tangent, -7 would have been it, and we would have been done. So now this becomes positive, right? Got the negative, positive. Now we have y minus 5 equals -7x minus 14, right? Got to distribute. And to finish it off, remember we want this, right? Remember slope-intercept form, y equals mx plus b. So, you add that 5 over, and you get y equals -7x minus 9. So that's your final answer right here. Remember, equation, don't just sit there and stop at the tangent line of -7 or tangent slope and say, I'm finished. No, it's asking for that equation of the tangent line. So yeah, you will have to go back to the point slope formula. Remember, x1 and y1, where do you obtain that from? That's the point that they initially give you. For these problems, they will always give you the function, and they will always give you the point that they want it to be tangent to. And it doesn't matter what your function looks like. All right, like let's try this one right here, like f of x equals square root of x plus 2, and we want it to be tangent to the point 7, 3. So it's a root, right? Don't freak out. It still works out the same way. We will still use these two formulas right here. Now, remember, when you start this, if you want, you can label this point, right? This is like your f of a. That way, to guide you as far as the substitutions right there. So if we plug that stuff in, m tangent, well, it's going to be the limit as x approaches a. What's a in this case? It's 7 of f of x. Well, f of x is just the base function, right? Square root of x plus 2. Minus f of a. Well, we have to find f of a, right? Got to find out what is f of a. F of a is equal to f of 7, right? Because again, a was 7. What is f of 7? Well, that is equal to the square root of 7 plus 2, right? Where am I getting this from? Because f of x was square root of x plus 7 in here for x. This is square root of 9, which is 3. So now we have that. F of 7 is 3. Whenever y'all do that f of a part, you should never be left with variables for this f of a because you're always taking f of some number. So you always be plugging a number into your function. Remember, that number is just the x value, right? It's the a, or it's the first number they give you from your point. In our denominator, we have x minus 7. So again, we have that issue, right? You're always going to have an issue with these problems because whatever number they're asking you to be saying the limit of, like as x goes to some number, that number will always make the bottom 0. So it's always going to make your thing undefined. So you're always going to have to manipulate your equation. Now, how do we do that, right? Well, remember when you had the root or some kind of root, the trick was to multiply by the conjugate, right? Got to multiply by the conjugate of that root. Well, the conjugate in this particular case is the square root of x plus 2 plus 3, right? So when we multiply, right, up top, we have a FOIL, right? Remember, this is the difference of two squares right here. What you can remember about that is that if you have, this chunk right here, this is just a plus b times a minus b. Remember, that was a nice little thing to FOIL out. That was the difference of two squares, right? This is just a squared minus b squared in the end. Now, if we apply that, right, if we apply that to this, right here, remember, this whole root x plus 2 is your a. Your b is a 3. So if I multiply this out, the a squareds, or a times a, remember, a root times a root, that are the same, the roots just knock out. So you're left with x plus 2. That's what we're left with. And then minus b squared, what was b? 3. So what's 3 squared? 9. So you have that. That's what you have left over when you FOIL it out. Again, that's from the difference of two squares. If you can't remember that formula, remember if you do FOIL, first, outer, inner, last two, you'll still wind up with this right here. Now, for our denominator, we're not going to FOIL that out. We want to keep it in factored form. So you may be thinking this still looks like crap because if I put the 7 in here, we still get 0 on the bottom. That is true. You still get 0 on the bottom, but keep simplifying. What happens? We now have x minus 7 up top. Because 2 minus 9 is negative 7. On the bottom, we now have x minus 7 times the square root of x plus 2 plus 3. Well, now we can knock out the x minus 7s, right? You can knock those out. What are you left with? You have 1 over square root of x plus 2 plus 3. Now if we plug the 7 in, we're okay. Because we have 1 over the square root of 7 plus 2, and then plus 3. This is 1 over the square root of 9 plus 3, and that gives you 1/6, right? Square root of 9 is 3. 3 plus 3 gives you 6 on the bottom. That's where you get the 6 from. Remember, this is just the tangent slope. That's just m. We're not finished. We need the equation, right? We need the equation of this line. So where do we go from here? The point slope formula. So the m, we had a 6. 1 over 6. We have our x1 and y1. Remember, that was the point they gave us. They said 7, 3. That's x1 and y1, right? That's that point. So we have 1/6 x minus 7. Y1 is 3, so y minus 3. So we have that now. Let's simplify. Don't fear the fractions, right? We can do this. So y minus 3 equals 1/6 x minus 7 over 6. Okay, keep on going, right? We add the 3. This is y equals 1/6 x minus 7 over 6. So if I need to add 3 to 7/6, right? Got to have the same denominator. This is 3 over 1. But if I do LCD, this becomes plus 18 over 6, right? Where did I get that from? Because it's 18 divided by 6. It's still 3, right? You still got to know how to do that. Don't leave your answer like this. You got to combine these. Those are like terms. You can completely combine them. So what is the final answer or the equation? We have y equals 1/6 x plus 11 over 6. That is your equation right here. If you're not comfortable with that, doing that LCD stuff with the fractions, remember those little TI-30s, they have that ABC button, right? That's the fraction button right there. So you could say -7 ABC 6 plus 3, and it'll give you that right there. So don't forget, if you have a root and some kind of problem with limits and it's causing you issues, you most likely, like 95% of the time, you're going to multiply by the time you get. And if you do it correctly, that will let you get rid of the root, which is going to help you take the limit of that function. Because again, with these tangent problems, you're always going to have some kind of restriction or some kind of issue that needs to be handled algebraically somehow. All right, let's try another one. This will be the last one. Different functions. So here we are, f of x equals 1 over x, and then we're trying to create a tangent line at the point 2 comma 1/2. So again, if you want to start, you can label this, right? Like, oh yeah, this is f of a right here.
Question. So they give us f of a when you plug
Yeah,
in the.
right. They will always give you this right here. Correct.
they're- Are we
And
just cross checking there to see if it's correct?
yeah, you can, right. With all the other problems, if you jammed in those x values, it'll spit out the corresponding y value. Like right here, you can see it, right? If I plug 2 in, we get y equals 1/2. Or for the previous problem, the square root of x plus 2, if you plug 7 in, you got the square root of 9, which is 3, right? So it has to work out like that, right? It always will. All right, so now let's start this up, right? We're gonna have, gotta find that slope, right? That tangent slope. So that tangent slope is the limit in this case. As x approaches, a is 2, of f of x, right? F of x is just the initial equation, 1 over x. And then minus f of a. Well, what is f of a, right? Remember, we needed f of a. F of a, in this case, is f of 2, which is 1 over 2, right? It's just equal to 1/2. So now we have 1 over x minus 1 over 2. And on the denominator, for the denominator, remember we had as or x minus a. Well, a was 2 in this case. And look at it. Always have that problem, right? That will always have with tangents. When you plug this limit in that they want you to examine, the bottom's always going to become 0. So what do we do right here, right? Because you have 1 over x minus a half over x minus 2. It looks kind of weird. We have fractions over fractions. Remember, if you have fractions over fractions, that's just a complex fraction. That's all that means. But to get rid of the complex fractions, what we're going to do is we're going to multiply everything by the mini LCDs. Or mini LCD. What I mean by mini least common denominator is like this x and this 2. These are the mini denominators because they are fractions within, this is the big fraction right here. And if you want, you could say this is x over 1 and this is x over 1. So what you would ask yourself is, what's the LCD between all these mini denominators like x, 2, 1, and 1? So the mini LCD is 2x. Remember, it's just the product of all your unique terms, the product of all your unique factors in the denominators. Well, the only unique ones are x and 2. That's where I'm getting 2x from. Now, what are we going to do with that? Well, we're going to multiply everything by the mini LCD. So all of these, I'm going to take 1 over x and multiply it by 2x. I'm also going to take the 1/2 and multiply it by 2x. We're also going to take the bottom, because that's everything, right? We've got to take the bottom and multiply it by 2x. And minus 2 times 2x. Now, why do we do that? Because that's going to help us get rid of these mini denominators. How does that work out? Well, look right here. This is, remember, 2x over 1, 2x over 1. These x's cancel out. Just like these 2's cancel out right here. So what does that leave you with? That leaves you with 2 minus just x. Now in the denominator, nothing cancels out, right? So we have x times 2x. That gives you 2x squared. 2 times 2x is 4x. So remember, we're still looking at this limit as x approaches 2. We still have that issue of if we put 2 in the denominator, what happens, right? We still have a problem right there. Because we still get 0 on the bottom. So what can we do, right? What can we try to do right here? Well, we could do some kind of algebraic manipulation, right? So what can I do in this instance? Or what can I try to do right here? Well, is there a GCF for the bottom? Yeah, right, there's a GCF. We can take out a 2x. If we factor out a 2x from the bottom, what does that leave us with? X minus 2, right? We have that. That's a little better because if you notice, we have 2 minus x up top and x minus 2 on the bottom. But you cannot cancel these out because they are not 100% equal, right? They're almost there. They're almost equal. It's just what's different about them. It's their signs, right? You see how they're perfect opposites of each other, right? 2 up here is positive, down here it's negative. The x is negative up here, down here is positive. When you have that, what can you do? Well, you can factor out a -1 from one of them. So, like, what I mean, by let's look at this x minus 2. Yeah, this x minus 2. If I pull out a -1 from it, what happens right there, we get, that makes this a negative x plus 2, right? Because a negative times a negative, negative 1 times negative x is positive x, negative 1 times 2 is negative 2. So that was legal right there. And then I could say, well, wait a minute, this is negative 1 times 2 minus x. What did I do right here? I just changed the order, right? 2 is still positive, x is still negative right there. So same thing, it's the same thing right there. Why did I do that? Because now we can cancel, right? So coming back from this, right, we're just gonna go, this is 2 minus x over 2x. I'll keep that negative 1 right here for a second. And then 2 minus x. I'll put all this in there. So what does that allow us to do now? We can cancel out these 2 minus x's. What are we left with? We're left with 1 over negative 2x. Now we can plug 2 in, right? Because remember, we were being asked what's the limit as x approaches 2. And what does that all equal in the end? That would be negative 1/4. Now we're not finished, right? That's just the slope. So what do we need to do now? Go to the point slope formula, right? Y minus y1 equals m times x minus x1, all that good stuff. So remember, x1 and y1, that was our point, right? Remember we had 2 comma and a half. So we're going to have y minus, watch the signs, 1/2 equals m is negative 1/4. X minus 2, like that. Now we have y minus 1/2 equals negative 1/4 x. What's 2 times negative 2, sorry, times negative 1/4? That is a positive 1/2, like that. And then we're gonna add, right? Add this 1/2 to both sides. So we get y equals negative 1/4 x. And then a half plus a half, that's easy, right? That's just 1, right? So there's your answer. So again, please don't stop at just finding the slope, right? A lot of people on the test and stuff, when they take them in class, they would tend to stop right here. And it's like, no, read the directions, right? The directions saying give the equation of a line tangent to. So remember, this only gives you the tangent line, the tangent slope. Then you have to go to the slope intercept or point slope formula to find your equation. And of course, when you're finding these tangent slopes, you're always going to have that issue of trying to get rid of the 0 from the denominator. And as you can see through the problems that we've done, it usually involves some kind of algebra, like factoring, multiplying by the conjugate. Or in this one, we had to multiply everything by the mini LCD to remove that issue. And then we also have this factoring out a negative 1, right? So remember, if you see 2 terms that are almost equivalent, right? Like if I had, like if I had 4 minus x and then x minus 4, right? These two are perfect opposites of each other. 4 was positive here, 4 was negative right here. X was negative right here, X was positive. If I were to take, and it doesn't matter which side you do it to, like if I factor out a negative 1 from this, I would get the 4 minus X. And then you see that's how you do that. How can you test to make sure you have the right signs? Do your work backwards, right? Multiply this through. Negative 1 times 4 is negative 4. Negative 1 times negative X is positive X, right? So again, if you're in doubt about, did I do that? Did I do this little weird trick correctly? Work backwards, right? Because as long as it algebraically makes sense, you should get back to initially to what you started with right there. That's another little important trick that can pop up with these problems. So that wraps up this section right here. Like I said, your test will be next Wednesday. It will unlock at 4 o'clock, so like we wouldn't meet on Zoom at 4 o'clock, like y'all just knock out your test and stuff. And then at 5:15 we would start up class and we get on here pretty much. That's how it would work like that. But do y'all have any questions about this right here? Remember, if y'all working. Yeah, go ahead. Go ahead. Question?
The test, it's only on limits, or is it going to have this part in it as
Well, it's
well?
gonna have all this stuff, right? It pretty much, if you look on the homeworks, I think we go up to, it's to 2.8, so one more section. So it's gonna cover all that stuff like that. But it's only 14 questions, and I know people are thinking 14 questions in an hour. That I'm not gonna have enough time to do that. But there are some problems where it's like just look at the graph and then what's the limit as X goes to like 2 or something, and it's like some of them are multiple choice. So if you know what you're doing, you're gonna be able to do it in like 10 seconds on the problem. So it's about 14 questions, and you have an hour, and it'll cover 2.2 through 2.8 like that. Any other questions? Remember, if y'all are working that web assigned stuff, definitely, and you have issues, you can go out there and ask the question, click the instructor button, ask me, or hop on the Zoom office hours. I am on here and stuff, and we can work out the problems like this. So there are no further questions. Y'all have a good night, okay? Bye.